Alright, let's finish this video, then watch the other.
Because I said so.
Because Mr. Levin said.
Well, you can do it by this, you can do it by the rule, or you can think that is just a linear function, right? Derivative of a linear function has to be the constant term which is in front of it, which happens to be a 1 in this case. That's going to be 1. If that had been 3x, that would be a 3.
Oh yeah, we left off on that
This one.
question.
That's a constant, that's gone out of your problem. How many people made it that far? Yes, no, yes? Good, all right, cool. Now the next one asks this, can you take this idea and apply it? At what points does y equals x cubed minus 3x plus 4 have horizontal tangent lines? Tell me something about a line that is horizontal. What do you know about a line that is horizontal? Slope is how much?
0.
Okay, the slope is 0. You're all right. Horizontal tangent lines have slopes that are 0. You follow? What will give you the slope?
Derivative.
We know derivative means slope, right? So the idea is, can you find the derivative and see where it equals 0? Because if you can find the derivative and see where it equals 0, you will have the points at which you have horizontal tangent lines. This is, you will find out.
I couldn't finish this at the end. Third. Wait a minute. Is it not this? I think I was doing something weird yesterday. It seems pretty easy actually. What would the y be? One square root of 3 cubed minus 3, 1 square root of 3 is 4. I don't know, it'd be some y, but I don't want to go through this if I'm wrong. So I'll just see what Professor Leonard says.
Use some graphing for finding out the points of relative max and relative min. You ever heard of those things before? We'll be able to do that very quickly. We'll be able to optimize word problems, maximization, minimization, cost functions, all sorts of things with this idea. Find derivative, set equal to 0. That's going to give you the points that you get a horizontal tangent. We're going to talk about this next. All right, so one question that we can conquer, according with our derivatives, and the idea that a derivative is a, what's a derivative again?
Slope of a curve.
Good, glad you're awake today for Tuesday. Congratulations, that's awesome. We can conquer the idea of, can we find out where functions will have horizontal tangent lines? Firstly, what do you know about a line that is horizontal? Something about its slope.
Slope is 0.
Slope would be 0 for a horizontal line, true? So if we were trying to look for lines that are horizontal to our original function, how do you find the slope of the original function? A derivative would give you slope. Yeah, absolutely. So if we found the derivative of our original function, and we found out where that was equal to a slope of 0, then we're going to be able to find the points where we have a horizontal tangent line. Here's how you would do that. Number 1, take your derivative of your function. Go ahead and do that now.
Wonder if my derivative was right. Oh, this is an easy one. I got it right.
So do dy dx, or y prime if you'd like. Take your derivative. Come on, we got this last time. Take your derivative.
Let me make sure. Wait, would this be minus 3? Hold on. Because if you split this up, 3 times the derivative of negative x. Which would be 3 times negative 1. Oh, is this negative 3? Crap. I think it might be. So that would mean this is 1. Hold on. X squared equals 1. X equals plus or minus 1. Oh. Okay. And then that's easy to plug in. Plug in a positive, you get 1 minus 3. Negative 2 plus that's 2. Negative 1. It's a odd exponent, so it's a negative. It stays a negative. Negative 1 minus negative 1 plus 3. 2, 6. I think.
Derivatives now should be, oh man, this should be really quick. Shoot, if we had to do the limit for this derivative, that'd take forever, right? It wouldn't be that great. But now we can do it in literally like 5 seconds. Like literally 5 seconds, crazy. What's the derivative for y equals x cubed minus 3x plus 4? What is that?
3x squared minus...
Great, because I told you you can take it term by term. 3x squared, absolutely, minus how much? 3. What happens to 4? That's a constant. Derivatives.
Okay, that's what I got, yeah.
Constants gives you 0.
I don't know how I got minus
It's not
1.
attached to
I'm
a
tired last
variable. Did you get 3x squared minus 3? Okay. What does this give you again?
Formula for slope.
So this right here is your slope. Of that curve. That's the slope of that curve. What I want to know is where this curve has tangent lines which are horizontal. What we found out earlier is that the slope of the tangent line is the slope of the curve at the point. Does that make sense? So if this is the slope of the curve at any point, and we want that slope to be 0, can you set that equal to 0?
Yeah.
So if you set this, the idea is we want it to be horizontal, right? Horizontal means a slope of 0. So basically we want a slope of 0. 0 means horizontal.
Can you do that for any slope you were looking for? Say if you wanted the slope where it equals 2.
Absolutely. So if I want a slope of 1, I'd have it equal to 1. Probably be harder to solve in this particular case, but you can do it. Yeah, this is a formula for slope, so if we set it equal to whatever we want, now the idea is we're typically going to pick horizontal because interesting things happen when you have a slope equal to 0. That really does have interesting things. For instance, this. At this point up at the top, notice positive slope, positive slope, positive slope, negative slope, negative slope, negative slope. Do you see that? Therefore, at the top, it has to have a slope of 0. That would be a change from increasing to decreasing. That would give you a relative maximum, sometimes an absolute maximum of your function. So interesting things happen there. Curves are optimized normally when you have some sort of a slope equal to 0. So this is going to be the most common question I'm going to ask of you as far as relate the slope to some number. It's typically going to be 0. You follow the idea? Now can you solve that? Hey, that's just some basic algebra. So if we solved it, how might you solve it?
Factor out 3 difference of squares.
You could. You could do factor 3 difference of squares. You're going to get 1 and negative 1. Do you see it? Or if you added 3, divided by 3, and took a square root, you'd still have 1 and negative 1. Do you see it either way? So either way, because when you take a square root, you have plus and minus. I like the factoring version. Sure, we get x squared minus 1 equals 0. That's 3x plus 1, x minus 1. X plus 1 equals 0. X minus 1 equals 0. Therefore, x equals negative 1. X equals positive 1.
I didn't think about doing it that way.
Hey, do something for me real quick. Just verify this for your own edification here, for your own knowledge. Take those, plug it into that. take these and plug it into that and see what you get, okay? Just so you see what happens here. Take a -1 and plug it in. How much do you get?
0.
You get 0. Take 1 and plug it in. How much do you get?
0.
So would you agree that these are the points where your slope is going to equal 0?
Yes, sir.
These are the points where you're going to have a horizontal tangent. These are actually not the points, I misspoke. These are the x values. Can you now find the points
Plug them into the function.
at which you will
the
have a
original
horizontal
function.
tangent? The points. These are your x values. How do you find points? To this one?
No.
No, that gives you slopes. That would give you points. So the points would be at, all right, well, let's see here. If x equals -1 and x equals 1, if I plug in -1 and I plug in 1, these 2 points will have horizontal tangent lines. Plug in -1, how much do you get out of that? 6? Okay. Plug in +1, how much do you get out of that? Those right there are the 2 points where you will have horizontal tangent lines. Nowhere else. That's it. I can say for certain nowhere else because we have found the function for the slope. We set equal to 0 and we solved it. And these are the only 2 points that existed. That's it. How many people understood the idea of a horizontal tangent? It's kind of interesting, right? Kinda cool. Last thing in our section really is we can also talk about higher derivatives. We've been taking first derivatives this whole time, which means you take the derivative of the function and that's it. Right now I'm going to tell you that you can take a second derivative and a third derivative and as many as you want to take. So we're going to look at higher derivatives.
Really? That's odd. Very strange.
I do need to tell you the notation though, how we write out a first and a second and a third and a fourth. So here's a first derivative, second derivative, we'll talk about a third, and you can go further and further and further, however many derivatives you want to take. Our notation for a first derivative was typically this, f prime of x, you remember that one, right? Or we'd have
ddx.
y prime, you can write y prime,
Oh, yeah.
or
dy,
dx. Those are the main 3. We stick with those normally. Actually, in this class, we'll be sticking with this one, and that one typically is where we like to go. You all right with that so far? That should be like old school stuff. Well, not old school. It's all new for you, but like from the previous section. So we have that. Second derivatives say this. You take your first derivative, then you take a derivative of that. So for instance, could you take a derivative of this? Yeah, it'd be pretty easy. You'd get how much? You get 6x. Very good. That would be called a second derivative. Second derivatives are notated this way. So this is the f prime of x. You'd say f double prime of x.
Double prime.
If I took another derivative, I'd have f triple prime of x. And you just keep on writing little dash marks. Some people I've seen put a little 4 up there for fourth derivative. Although we rarely get to a fourth derivative, but you could. But you keep on writing those little dash marks. This is called the Newtonian method of writing derivatives. You see, there's these 2 guys, Isaac Newton and Sir Godfrey Leibniz, who invented calculus about the same time. One of them was English. I think Newton was English, wasn't he? Mm-hmm. And then Leibniz was German. And of course, back then, the nations want to say, well, we invented calculus. This is ours. And so they kind of stuck with their own notation. And this right here is the Newton's way of doing it. He used little dots. And this is the Leibniz way of doing it. And we still have that notation to this day. So this comes from the German guy, and this comes from the English guy, how they notated it, and we still use that. And each of them have their advantages. This one, I'll show you some advantages to this later on, why it's kind of nice and why I do it this way. First, because of my German heritage, you know, but then, no, I'm just kidding. Because we actually can do some pretty cool things with this type of notation. I'll show you that, especially when we get to like differential equations, things like that. All right, now y prime, you'd still stick with the y double prime, y triple prime, and so on. The dy dx does this, a little bit different. It says, okay, this is a first derivative of y with respect to x, okay, one time. This says, take a second derivative of y with respect to x both times. That's how I think of it. So you have a little 2 saying that's a second derivative. This is a third derivative with respect to x every time. So we keep on putting on another number. That's a little bit more concise than those little dash marks. I like that a little bit better. It looks better. You can see it more. It have like, also if you're going through and you just, oh, lost one, well that would suck, right? Because then you don't know. But it's hard to screw up a 2 and a 3. Well, maybe not that hard. But harder than messing up a dash mark. Are you guys okay with the derivative notation? First,
Yep.
second, third. What I'd like to do now, just for fun, can you find all of the higher derivatives of this?
Probably. It's 3x cubed minus 5x squared plus 9x minus 347. Okay. F prime of x. 4 times 7 is 28. X cubed minus minus 9x squared minus 10x period plus 9, and that's it. Find the second derivative of double prime of x. That's 28 times 3. 84 x squared minus 18x minus 10 f triple prime of x equals 168 minus, or 168x minus 18, and yeah, should be it.
Can you find all the higher derivatives there?
Oh, all of them. So maybe he wants to go further than that. F quadruple prime of x. 168 f. I guess he said some people put 4s up there, so I'll do that. F I don't know, 5 prime of x equals 0. So that'd be all of them.
So start with the first derivative, find the first derivative, then find the second one, then the third one, then the fourth one, then the fifth one, then the sixth one, and see what happens, okay? I want you to keep going.
So it seems like all derivatives, if you keep finding the derivative of the derivative, it seems like they all become 0 at the end.
Did you find them? Are you still working on it? You're still working on it? Keep going. If not, well, let's start up here. First derivative, can you please tell me what the first derivative is on this? 20x cubed. You got that one, right? Okay, then I heard 27x squared, yes? Minus 10x.
9x squared.
What did I do?
9x?
Oh, 27. I actually cubed it. My bad.
Oh wait, yeah. What's he doing?
I was on this one. Shoot. I guess 3 times 3 is 9. That's good to know. Yeah. And lastly, what else do we have? Yeah, my bad. What happens with 347? What?
Then it goes away.
Here's what's interesting too. What if I made this 34,755? Would this derivative
Doesn't
change?
matter.
So that constant really has no effect on your derivative. That we're talking about the slope, right? So all this is really a shift upward or downward. So if we're just shifting the whole function up or down, it doesn't affect the slope of the function. It says, oh, now it's way up here, now it's way down here. So that really doesn't affect it, which is interesting. Okay, next up, second derivative. We just take the derivative again. So we're going to do, what's 28 times 3? What is it? X squared minus 18x, you got that one right, minus 10. What happens to the 9? It's a constant. It goes away. Now what? Okay. Then we take the derivative again, and yeah, we're going to get 168, and again, that constant goes away, 168. Well, let's do the fifth derivative. What's the derivative of 168?
0.
What's the sixth derivative? What's the seventh derivative? What's every derivative after that? This is going to happen for every polynomial. You see, at some point, no matter what you start with, if it's a polynomial, you'll be able to take a derivative, and what happens every time is the order of the polynomial decreases by 1. So 4, 3, 2, 1, 0, and then a constant. So that's going to happen with polynomials. Now, does it happen all the time?
Probably not.
Think about something that's not a polynomial. I'll give you an example if you need one. How about that? Well, decreasing, because we subtract 1,
Oh,
it becomes
yeah, keep
more and more
going.
and more negative, right? This derivative the derivative of that would give you negative 2, x to the negative 3, right? Then you get positive 6, x to the negative 4, and then so on, and so on, and so on, and so that actually, that exponent keeps on getting smaller, more and more and more negative. So this won't cycle out to 0 eventually. It's not a polynomial. So be careful on it. You're not always going to go to 0, but you can find more and more and more derivatives on this. How many people feel okay with our higher order derivatives? So it's basically just take a derivative and then take it again and again and again. That's what this is asking you to do.
So where would be the correct place to stop at 168 or when it reaches 0?
0. This is all the higher derivatives because every other derivative is going to be 0.
So 0 counts as a derivative?
Absolutely. Yeah, this, we've taken 1, 2, 3, 4, but then you could take this again and get something different, right? You could get 5. But then as soon as you take it 6, it's not doing, you can take them as many times as you want. You're just going to get the trivial answer of 0 after that. Yes?
What if it was 1 over x squared?
That is 1 over x squared.
Well, then we get to 0?
No. No. The derivative of this is in no way 1 over 2x at all. You're breaking the rules here. There's only one rule that we have. The one rule that we have is it
You can break
must
apart
fit
terms.
this format, folks. It
Or you
must
cannot
fit
break
this
apart
format.
terms. You can,
If it doesn't fit that format, you can't do it.
because that's
it.
one
You
term,
need
so
to
you
be able
can't
to break
mess
it
with it.
down in such a way that it does fit this format. All we can do is separate by addition, subtraction, and pull out constants. So in order to make it fit this format, we can't just say, oh, derivative of x squared is 2x. That would be awesome, but no, it doesn't work that way.
it's
Instead,
gotta
you say,
fit that
oh, this
format.
is the derivative of x to the negative 2. That fits that format. Do you see the difference there? You have to make it fit that. So you have to pull that negative, that exponent up and make it a negative. That way you can work with your power rule. Does that clarify your question? Okay, so we can't just take derivatives of parts of like quotients. Can't take it of parts of products. We're going to talk about those things in just a little while, but you can't just do that. You with me on this? Would you like to see one more example? Might be good for you guys to see this one. take the derivative of all those things?
What is that, dude? Huh. We can only separate them by addition and subtraction. So I wouldn't know what to do with that.
Could you take the derivative of this thing?
On its own.
Yes, you can. Yes, you can. Can you take a derivative altogether? No, not the way it is right now. Let me show you a couple things about this problem. Number one, well, you
I mean, I could see you could make the square root into 1/2, but that still wouldn't help.
probably are going to want to make this x to the 5th minus 2x minus 3 all over 3x to the 1/2. Do you see what we did there? You okay with that? That's okay. That's great. That's fine.
Still messed up there.
But here's what you cannot do. This is going to go back to our previous problem. What you can't do, folks, you can't do this. I wish you could, but you can't. You can't go, oh, you know what? This is 5x to the 4th minus 2x over 3/2 x to the negative 1/2. Do you see what I did? I took derivative, 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 derivative. Can you do that? No.
Nope.
No, you can't. They're connected. They're in a quotient. We're going to find out later you can't do that. You can't do that one. If you want to write that down, cross it out. If you wrote it down, cross it out. You can't just take it piece by piece if they're connected. You have to be able to separate them completely and take a derivative term by term. You can't do that here. You see, you can't separate this and have its own derivative, minus its own derivative, minus its own derivative, and then have it over another derivative. That's something we can't do. We can't do that. So what we would have, oh, give me another option. What could I do? Whenever I have some expression over one single term, what could I do? I can't move that up. I don't want to do that.
Only thing I'm seeing is that you can split this up to like x to the power of 5 over 3x half minus 2x, and then yeah, and so on. But you still have fractions and all that. You can't do the conjugate because it's one term in the bottom.
What can I do when I...
Factor or something? No. Well, wait. Hold on. What if you went like... If you factor out like a half or something? I don't know. There's still a -3 there. I don't know, man. Yeah, I don't know.
Whenever I have several terms over one single factor. One
Split
single
it up.
What now?
Split it up over the...
Let's split it up. So sometimes these daunting looking derivatives that you need to do, what would happen if I did split this up as x to the 5th over this, minus 2x over
that is
this,
the answer.
3 over that. Let's see what happens.
I didn't think that would help. Minus 2x over 3x to the power of half. Minus 3 over 3x. Okay. Well, if this, you can cancel out a 3. With this, factor out an x, a half an x. Would that help though? I don't know. Let's see what. I don't know if you
There,
factor at
then
this
maybe
point.
we'll make it fit into our scenario that we.
Oh wait, what? Oh wait. 3. What would this be? I don't know how you'd make that fit.
Firstly, are you okay that this
Let's see
doesn't
what he's
work?
getting at though.
As a matter of fact, you can't just take all these pieces if we have a quotient or a product or something crazy. The only time we ever found out that that did work was this. Look, when I had a polynomial, yes, that works. Because I can separate by addition subtraction, that's what makes that work. I didn't tell you you can separate by division because you can't. I didn't tell you you can separate by multiplication because you can't unless you have the constant that comes out. That's the only thing. So you can't separate by division. You can't do that. Only thing you can separate is addition subtraction. You follow me on this? So when I translate this into 3x to the 1/2, we gotta have something better than this over that. That doesn't work. What we could do is potentially split these up into 3 different fractions. So for instance, why don't we try to make it x to the 5th over 3x to the 1/2 minus 2 over 3x to the 1/2 minus 3 over 3x to the 1/2. And then we'll try to simplify each of those fractions to make them fit in our power rule and then take the derivative. Are you guys all right with what we're doing so far? We're
Yeah.
trying to make it fit into this. We have to make it fit there. If we can't make it fit there, we can't take the derivative right now. Can you combine those? X to the 5th and x to the 1/2? How do you combine those?
Oh wait, subtraction, right? Oh. Would it be like this? Wait, what do you do if the this would be a third, wouldn't it? Third x minus 2/3 x half minus x half. I didn't think about that.
Okay, what happens when you have common bases that are being divided? Do you add exponents, subtract
Subtract.
exponents, multiply exponents, or divide exponents? Let me break it down even easier for you, okay? Watch. No, just watch. There. Can you simplify that?
Half x.
Please, goodness, say yes. Please say yes, Mr. Leonard. I know how. I'm supposed to be in this class. Yay. How do you simplify this? What is it? What is it? You subtract what? Subtract your exponents, because when you divide exponents, you have 4 of them here. You have 3 of them there. You cross out 3 of them, you have 1 of them left, right? That's subtracting exponents. You go, oh yes, this is completely gone. That becomes an x. What happens to the 2? Go on the top, stay on the bottom. So you would have x over 2, true? Or you could get 1/2 x.
Yep.
Do you follow? Okay. So you know whenever you have common bases, you subtract exponents. This is not a hard concept. You've seen this since your beginning algebra days. So can you combine these? The answer is what? How do you combine those?
Just like you did up there. Subtract them.
How did you combine those? Subtract what? Subtract your exponents. What's 5 minus 1/2? How much are you going to get?
4.5.
4.5. Give it to me as an improper fraction. 9/2. Really? All right. I believe you. I didn't do it in my head. Yeah, 9/2. I need you to be able to get there. That's not calculus. Okay, that's algebra. This right here, I mean, people have said before, you take calculus to finally fail algebra. Don't let that be you. Know your algebra. If you know your algebra, this is a piece of cake. I mean, really, honestly, calculus is easy if you know your algebra. I promise. And trigonometry. If you don't, yeah, it's going to hold you back a lot. Are you okay on, firstly, going from here to here? Secondly, going from here to splitting them up. And now thirdly, do you see how to get from the x to the 5th over x to the 1/2 into 1/3 x to the 9 halves. We're subtracting those two exponents. Do that in calculator if you want to. 5 minus a half, you're going to get 4.5 or 9 halves. Minus. Let's look at those numbers. That's going to give me 2/3. X over x to the 1/2 gives you what, please?
X to the 1/2.
1/2. Good, because you subtract 1 minus 1/2 and get x to the 1/2. Minus, oh, what's that become?
Like that. X to the 1/2. What is that, dude?
This is supposed to be a new video. You have that old school ringtone on? Come on, man. Give me some 50 Cent or something. Oh, that's even old, too. What's new? I'm only a...
How old is this video, man? 2012.
Edge of glory. Give me that one next time, okay? All right, thanks. What happens to the 3's? They become a 1. What happens to the x to the 1/2? What are you going to have to do with that in order to make it fit that? What do? Can you leave it like this and take a derivative?
Nope.
That would be the scenario. That would be that scenario. What do you have to do to that 1/2? So we're going to have to move that to the numerator and make it a negative 1/2. Do you follow me?
Oh, yeah.
You're
So
constantly
forgot about that.
trying to make it just look like that. That's what you need. So 1 over x to the 1/2? No. X to the negative 1/2? Yes. Yes. Show of hands, how many people feel okay with this so far? Simple algebra, good. All right, simple. You passed simple algebra. Very good. Hey, now that y, this is...
Alright, now we can find the derivative. So, what would this be? 9 over 6? 1.5? X? I guess improper, that would be 3 over 3 halves. 3 halves x. 7 halves minus 2. It's a third. I'm slow at this, my bad. Negative half minus half x. Negative be 1.5 or 3 halves. I think. And what are we using for the derivative here? It doesn't say. Alright, I'll just use dy dx. Alright.
Still, why? I haven't even done, did you notice I haven't even done calculus yet? No calculus yet. This is basic, this is algebra. Now can you do the calculus? Can you take a derivative? Why don't you carefully, right now, take me that derivative? Go ahead and do that. Carefully take the derivative. I'd rather have the... Go slowly on it, by the way. I want the correct answer slowly rather than the wrong answer quickly. That would be stupid.
That'd be very frivolous.
Was that Lady Goo Goo, by the way? That lady?
Yeah.
Is that not right?
That was perfect. Spot on.
So dy dx or y prime if you like. Note how each of these now fits into our format here. The constants, we could pull them out. We're just taking a derivative of x to the 9 halves, derivative of x to the 1/2, derivative of x to the negative 1/2. Let's do that piece by piece. I'm going to show you every step, okay, right now, so you see where it's coming from. I'll have the 1/3 times the 9 halves. You see where the 9 halves is coming from, ladies and gentlemen? Okay, I'm going to have x to the, I need to do 9 halves minus 1. That's going to give me 7 halves. Did you get 7 halves as well? Perfect. 7 halves. Get that one? Next up, I'm going to have minus 2/3 times what, folks? Okay. What 1/2, because that's my exponent that I'm bringing down. So I leave my constant alone. I'm multiplying by my exponent, and then I'm going to take x to the 1/2 minus 1 gives you what? Lastly, I have minus. What now? Okay, -1/2. Okay, great. So -1/2. I'm going to put that in parentheses saying, hey, I'm a negative, watch out. I have a negative there. So minus is minus, negative, that's our negative. X to the, okay, x to the, what am I going to get? -3/2. Because I had -1/2 or -3/2, right? We use improper fractions here because they're easier to deal with. So -1/2 minus 1 gives you -3/2. You got that one? Show of hands, how many would feel okay with getting that far our problem? All right. Let's make it a little bit prettier. Simplify some fractions.
Yeah, this would be plus half x.
That's 1.
I got kind of close. For doing it, missed in my head.
That's 2. There's a third one.
Nice.
In the most basic sense, that's your derivative. No problem. What is that? What did I just find? What is that we found? Oh, come on.
The slope of a curve at any point. And if you plug any x value in, you'll get your slope for that x value.
What is it? What's the derivative? Slope of a curve. Now, the slope of this curve, this weird curve, at any point. It's kind of neat that we're able to find that, right? We don't even know what the curve looks like. Yet we're able to find the slope of that at any point. We have a function for it. Now, if you do want to make this a little bit nicer looking, you can translate these back into roots if you really so desire. You could do, well, I probably wouldn't change that one at all, unless you want to do a square root of x to the 7th. That's what that means. So if you really are forced to do it, here's how you would change this back into roots. For me, most of the time that's going to be fine, but if you're forced to plug numbers in, you want to see what's actually going on here. So this would be 3 square root x to the 7th over 2.
I'm doing this.
Minus, since that's a negative, it will be on the denominator of fraction, 3 square root of x. Since that's a negative exponent, it will be on the denominator of a fraction along with that 2, a square root of x cubed. That's the way you would write that without any negative exponents associated with them.
But for your class, maybe we just leave it.
Most of the time, we're going to be okay on that. However, typically, if they get root form, you want to make it back into root form. So in that case, that would be maybe what you see in the back of your book, or some other context. Some people feel okay with our example up here. So, can we do this term by term by term by term? Can we do that? No, we cannot separate division. We can't do that. What we can do is separate our fraction firstly, then simplify each of those, and then take a derivative. That's something we can do. And that it's not too bad. We've dealt with a lot of fractions here, but I mean, that's some algebra. We should be okay with our fractions. Are there any questions before we move on at all? Do you like this derivative business? Can you imagine taking the limit of that? Of x plus h? Woo. Good thing we had that. Seriously? I'm only kidding. Are you ready to try some more advanced things with derivatives? See how we can really use this stuff. You ready?
Yeah.
Answer's usually yes, because we're going to do it anyway, so may as well be happy about it. 2.3.
I'll try and finish this.
Today you're going to learn some rules. You're going to learn about the product rule and the quotient rule. here's the scenario. Let's suppose that we start with two functions. I'm going to give you some very basic functions. F of x equals x squared. G of x equals x cubed. Here's what I want to know. Is it possible to take the derivative of one function times another function?
Well, wait a minute. That's kind of confusing. Because I thought you couldn't split it up using multiplication or division. I guess this would be different? Because I guess it doesn't matter. I don't know, I can see this going both ways. He's probably gonna say yes, because, I mean, I see where he's going with this, but...
Notice how this is f of x and this is g of x, right? The question is this. The question is,
Yeah, I'm not too sure on that.
is this equal to this? I need more room. I want you to really write that down and contemplate it.
Well, I guess I could just do it. Find out. This is times. So the derivative of f of x would be 2x. 2x times 3x squared. So you get 6x cubed. And if you multiply them together, you get x to the power of 5, 5x to the power of 4. Wait. Yeah, it would be 5x to the power of 4, wouldn't it? So is that right? You can't do it? I'm gonna say you can't do it then.
Is that true? Question is, can I do it? Can I break up derivatives by multiplication?
No.
Can I
Said
break
you
up
can't
derivatives
before.
by multiplication? Can I say, oh, the derivative of f of x times g of x is the same as the derivative of f of x times the derivative of g of x? Can I do that? I don't know. We have no idea. I mean, I'm just asking you right now. But I can tell you this. If we can find one example where it's not true, then this whole scenario falls apart. So what we're going to look at is, let's look at this example and see if it's true for this. Now, I'll tell you right away that you could get x to the 5th right there, couldn't you? So
Yeah.
we know for sure that this is true. This is the same as d dx of x to the 5th. What's the derivative of x to the 5th, ladies and gentlemen?
5x.
So we know for sure that this is supposed to end with 5x to the 4th. Do you believe me?
Yep.
Yes, no? Okay.
Yeah, there's
Okay.
no way this is true.
Let's try this way. Let's try to do it. The derivative of the first times the derivative of the second. What's the derivative of x squared, our first?
2x.
What's the derivative of our second?
3x squared.
Is it the same?
6x squared. No.
We get 6x cubed. Okay,
Cubed,
we
yeah.
got two different answers. Which one is right?
Wait, no.
5x to the
No,
4th
yeah, it
or
is cubed.
6x to the 3rd?
I
Which
got
one's
cubed
right?
too. Yeah.
You should know. You should know right now which one is right. Which one is right? This one?
No.
This one. Which one's right?
Well, which one's right? Well, if you're finding the derivative of x fifth, then I don't know.
Is this for sure equal to x to the fifth? Every time. Every time. Do you know how to take the derivative of x to the fifth? Every time. We know for sure that this way was right. What I'm trying to say is, do you end with the same thing? I know for sure, guys, for sure, this is the right way. It gives me a correct answer. The correct answer is 5x to the fourth. That's the correct answer. Is this the correct answer then?
No.
No. So does this way work? So can I separate derivatives by multiplication?
No.
No. Is this true? No. No bueno. No, you can't do that one. That's not true. You can't separate derivatives by multiplication. So what are we supposed to do when we get these functions that are multiplied together? We either have to distribute them, or we have to find a better way, and that way is called the product rule, which is the name of our section here. We're going to look right now at how we actually do the product rule. So, product rule. Product rule says, well, if this doesn't work, what is the correct way?
Dang it.
What do you do if you have one function times another function? You're trying to find the derivative of those things. Well, here's what you do. This is our rule. If you want the proof of this, come and see me. I'll give it to you. It's a little bit too long for our class. I usually will prove the things, but I'm not going to prove the quotient rule or the product rule for you. Unless you just come and see me, okay? So product rule says, here's how we're going to go about taking the derivative of a product. We're going to take the derivative of the first one, the first function, times the derivative of the second function. I'm sorry, the derivative of the first one times the second function, plus the first function times the derivative of the second function. I'll write that out in symbols so you see it. You take the derivative of the first function times the second one. You leave the second one alone. You add to it the first function left alone times the derivative of the second. You've still taken the derivative of each one, but it's different than this. You have that addition in there, that product. I like to think product plus. P goes with P, product plus. So we're going to have that. You're going to see in the quotient rule that we're going to have a minus sign in between there. So product plus. Associate the product with a plus. By the way, would it work for over here? Let's check real quick just to verify, okay? So d dx of x squared times x cubed. Again, we're supposed to end with 5x to the fourth, right? That's what we're supposed to end with. If we do this, here's what it says. Watch what the product rule says to do. It says...
Try it. So it would be x squared, or 2x times x cubed plus x squared times 3x squared. You get 2x to the power of 4 plus 3x to the power of 4, 5x to the power of 4. And that is what we got last time, right? Yeah. Nice.
As you take the derivative of your first function, that would be x squared. You find the derivative of your first function times the second function. That's how to write that out. It says you find the derivative of your first function times your second. Are you okay with the notation? Derivative of your first function times your second function. Then you have a plus sign. Then you write your first function times the derivative of your second function. In English, it says derivative of the first times the second plus the first times the derivative of the second. Let's see if it works. What's the derivative of x squared? So this becomes 2x. Oh, ladies and gentlemen, do I need to take the derivative of x cubed in this case right here?
Nope.
You follow the ddx. That's why I like the ddx. It says this is what you're taking the derivative of. That's why we're going to write it like that in this class. Go, oh, this says take the derivative of this one, but don't take the derivative of this one. You're only taking the derivative of whatever's inside your brackets there. Do you see it? That's why we use that. It says, oh yeah, okay, derivative of x squared, that's 2x, times x cubed, plus, do I take the derivative of this x squared?
No.
How about this x cubed?
Yes.
Yes, that's why I said ddx. It says take the derivative of that. That's 3x squared. If we make this a little prettier, we have 2x to the fourth plus 3x to the fourth. That gives us height. Are we right? Yeah, that works in that case. That's not a proof. That says it works for that example. You have to be able to prove it works for every example senior for that, if you want to.
Or we can just trust it works for everyone.
You can trust it. Yeah, you can trust it if you want. I would. I mean, it does. So, save me some time. But, so in English, the derivative of the first times the second plus the first times the derivative of the second. If you want to write that down, you can write that down if you like it at your leisure, or just watch the video again and hear me say it like 40 times. Just press rewind, okay? Derivative of the first times the second plus the first times the derivative of the second. And we will feel okay with that so far. Now, we're going to do one example on how to actually do this. I'll show you why it can be useful a little bit later on, how it really, really does help us out a ton, and why we need it. For right now, you're going to be wondering, well, why can't we just distribute all the time? For right now, we will be able to distribute all the time and get the same exact answer. I'll prove it to you right now. I'll show you. However, later on, you won't be able to do that. And so the product rule will become very, very important for us later. For right now, it's going to seem like, well, wait, hang on. Let me show you an example of this. Hey, look at my function. Do I have a product? Do I have
Yeah.
one function times another function?
Yep.
Sure, absolutely I do. I've got this function in parentheses times this other function. But do you see that I could distribute this?
Yeah.
Do you see it? If I FOILed this all out, I could do the derivative that way. I could do it for sure. I could do that. And so you might be wondering, why do we need this at all if I can always distribute? And the answer is, well, you can't. You can't. Or you probably don't want to. For instance, what if I gave you, now we're not there yet, I'm jumping ahead to give you a precursor to what we're going to be doing later. But here's why we need the product rule, okay? You with me on this? We're not going to do it now. I haven't showed you this yet. But what if this was to the fourth? Okay, do you want to distribute that 4
definitely not.
times and then distribute that one? Heck no. No, that's ridiculous. Okay, that'd be crazy. That'd take up more time than limits would do, all right? No, we don't want to do that. We want to find ways around that. The product rule is the way around that. Do you understand? That's the idea.
So it'd be good practice to start using the product rule now instead of.
Yes, absolutely. It's gonna, on your homework, it's going to ask you to do both. Do this 2 ways. And I'm going to show you next time how to do this 2 ways. I'll leave you with one. Don't pack up yet. I'll leave you with one more thing. But it says, distribute this, find the derivative. Then use the product rule,
Do it again.
distribute it, and then you're going to find out that you have the same exact thing, okay? So you're verifying that this product rule does work and distribution does work. You get the same exact thing. That's what kind of this idea was about as well. One last question. So a lot of people always ask me, so I'm going to answer right now in the last couple minutes. Well, hey Leonard, isn't this a product? 3x squared, isn't that a product? Well, of course it is. It's 3 times x squared. Yes. Why don't we use the product rule for this? If it's a product, why don't we use the product rule? Wouldn't it come out
It's way
different?
easier to do.
And the answer is, we kind of do use the product rule, but we cheat a little. Well, we don't cheat. We just don't show a part of it. Here's why. If you consider this to be a product, check this out. You'd have the derivative This would be your first, and that would be your second, true? You'd have the derivative of your first times your second, plus your first times your derivative of your second. All right, very good. What's the derivative of 3?
0.
0 times x squared. That's going to happen
Oh,
every
okay,
time
I
because
see.
that's a constant.
You don't show that
So
part.
if you consider that to be a product rule, the constant is always going to go to 0. So we really don't show that step, do we? We just show, oh, look at, hey, the 3's outside. That's why we can pull the 3 outside of our derivative. That's a constant. We can do that. It's product rule. It says, here's positive plus 3 times the derivative. That's 2x. That's 6x. That's why we can do that. Okay, so to answer any questions you might have in your head, why don't we have to use product rule? You really are. You're not showing it. We're going to start with that problem next time. So we're working on our problem. I'm going to show you that with the product rule, yes, there are other ways to do it, but ultimately we need the product rule because I think I showed you last time that we're going to have that if we have any sort of exponent here or here, we're going to need it because you certainly don't want to distribute that out 30 times if that's your exponent. That would be crazy. So how do we do this 2 ways? Well, way number 1 is, what if we don't even consider it to be a product at the very end? What if we distribute those parentheses and make it so we just have a basic polynomial in this case? Well, if we do that,
Try that my own. 3x to the power of 6 plus 2x cubed minus 3x to the power of 4 plus minus 2x. Okay. Finding the derivative. I guess I'm not gonna write that down now. Okay, the derivative of that would be 18x to the power of 5 plus 6x to the power of 2 minus 12x to the power of 3 minus 2. And then using the product rule, it would be x, wait, find the derivative of the first one. I'll write it out like this. Times 3x power of 4 plus 2x. I'm gonna shrink this so I have more room. And I think you add it. So we got x squared plus minus 1 times the derivative of 3x power of 4 plus 2x. So this would be 2x yeah, that's it, times 3x power of 4 plus 2x plus x squared minus 1 times 12x cubed plus 2. 6x to the power of 5 plus 4x squared plus 12x to the power of 5 plus 2x squared minus 12x cubed minus 2. 18x to the power of 5 plus 6x squared, or I'll put minus 12x cubed first. It's 12x cubed, 6x squared, minus 2. Yeah, I wrote it in a different order. This way seems longer, so I'm not sure what he's getting at. But I do understand if you had a 4 here, then yeah, you'd want to use the product rule for sure. Because it would take way longer to do it the other way. So yeah, same thing.
We'll get 3x to the 6th plus 2x to the 3rd minus 3x to the 4th minus 2x. Are you okay with that so far? Check for any like terms. Do I have any like terms?
No.
So maybe reorganize it just a little bit because that's the way we like to see our polynomials. And then the question is, can you take a derivative of that thing right there?
Yep.
Yeah, that's actually pretty easy. So if we do dy dx, what's the derivative of this polynomial? Can y'all tell me real quick? Thank you, all of you. Appreciate it. Let's all try this. What's the derivative of 3x to the 6th? Okay, minus what? Then? Uh-huh. Is that it? Okay, so that's our derivative. Now, the product rule should give us the same thing. And again, we're practicing the product rule in case I give you something like that, where you can't just distribute it. You'd have to distribute this one and then distribute. That would be very annoying. So we're going to verify with a couple of these examples that, yeah, you are going to get the same thing if you use the product rule. Do you remember what the product rule said to do?
Derivative of the first one.
First one?
Times the second one.
Sure.
Add the derivative of the second one plus the first one.
Yeah, that's very good. So there, I think the book has it in a slightly different order, but because of the commutativity of addition and multiplication, it really doesn't matter. As long as you take the derivative of one times the other, plus the other one times the derivative like a derivative of the first times the second plus the first times the derivative of the second. Or any way you kind of permute that, that's fine. Take the derivative of one of them times the other, then multiply times that one times the derivative of the other. In other words, for us, we'd say the derivative of the first function times the second function. So that's our separation of the product there. Plus the first function times the derivative of the second. So derivative of the first times the second plus the first times the derivative of the second. That's how we like to say that. That's like how we like to see that. Are you guys okay on how this is coming about? Again, we can't just take the derivative of this and this and this and this. That doesn't work. Anytime we have a product there, we have to use a product rule, or we have to distribute and do it term by term. So far, so good? Can y'all tell me what's the derivative of x squared minus 1? What are we going to get out of that? So this will be our 2x times 3x to the 4th plus 2x. Plus, do we take the derivative of this? This piece right here, folks? No. Okay, so x squared minus 1. Derivative of this. What do you think the derivative of
12x
that?
cubed plus 2.
12x to the 3rd, okay. Plus 2. Cool. Notice how you follow the ddx. That ddx tells you what you're taking the derivative of. It says the ddx of this, yeah, but not that one. Not this one, but yes, this one. So follow the ddx. You'll say take the derivative of this little piece. If you can do that for these rules, it will really, really help you out. Raise your hand if you feel okay getting down that far. Now, is this the same as that?
Not yet.
If we distribute it, it should be though. Let's find out. Here we'll get our 6x to the 5th plus 4x squared plus, we're going to have to FOIL that, right? Okay. Don't worry, we're not done. You're like, wait a second. Oh no. Oh no. Just wait. Just wait. If we FOIL this, distribute it, we're going to get 12x to the 5th plus 2x squared minus 12x cubed minus 2. Well, at least I see the minus 2. That's fine. You guys okay with the distribution? Just some basic algebra here. Now, if we do combine some like terms, I see a 18x to the 5th. Cool. I see a 12x to the third, minus 12x to the third. Gotcha. I see a 6x squared. I have minus 2. Got a minus 2.
Now, say we wanted to find the second or third derivative, can we just use that polynomial from that point?
Oh, sure, yeah, find the second one, bam. Just look, at these are the same derivative, right?
Right.
It is the same. This is just a different way to go about it. Of course, you, like I said before, could you distribute that and do it this way? Absolutely. For this one, that might be the easier way to go about it. It's a product rule with just one parentheses, but as soon as you have some exponents, everything changes. And you definitely don't want to do this if there's some exponents associated. So keep in mind, we're building up to things, okay? We're not there yet, we're building up to things. I'm giving you kind of like the groundwork for the stuff we're doing later. So yeah, you need to understand the product rule before we get to something that's called the chain rule, because then you're going to be using the product rule in combination with that thing, and in combination with the quotient rule, and in combination with these other ideas. So you do have to understand it, but I'm showing you right now that they are the same. It's just a different way to go about it. Do you guys understand the idea there? Also, have you read through the book, The Proof of this? The proof's in there. It's actually not a hard proof. There's just one little thing that they do. They add on an expression that equals 0 so they can factor it. And you can prove that the product rule works really well, really easily with that. So read through that if you haven't done that already. That's in this section. Read through the proof of the product rule and the quotient rule. It's not too hard to follow. I promise it's not too bad. Read through that. Would you like to try a couple more? Let's do one more with the product rule. I'll give you an example of how some of the problems in your book are going to look. That way you can kind of have a bearing to go forward with that. Then we'll talk about the quotient rule, and that'll wrap up our day today. So, the last example, just a straightforward product rule. It's not too bad. All it is you have to remember what this does. A derivative of the first times the second plus the first times the derivative of the second. Remember that. Be able to identify what products are, and then you're good to go. By the way, did I show you last time why we don't have to use the product rule for something like this, just that term, even though it's being multiplied? Did I show you that?
Yeah.
Okay, cool. Because when you do the product rule with that, the derivative of the constant goes to 0, and that piece falls out of the expression. Okay. Well, let's do that. 1 plus x squared, and then x squared. Firstly,
Okay. Probably going to want to change this to be x half, x to the power of half. X to the power of half plus 2.5, which is, hold on. That'd be 4 over 2 plus half, 5 halves. Something like that. if you use the product rule. Derivative of the first term. Wait, is he gonna add more?
You need to be able to see that this is in fact a product. Do you see it's a
I'll just keep doing it, I'm done. Let's see, 0 to x times, or let me write that better. Plus 1 plus x squared half x negative half 2 x, it's 1.5 or 3 halves plus half x. Oh wait, what am I finding the derivative of here? Did I already find it? Yeah, I found this one, okay. Half x negative half plus half x one and a half, 3 halves. It's got 2.5 x 3 halves, which is 5 over 2. Move this over. So it looks like the first one I found. And then yeah, half x negative half, okay. Again, it's harder to use the quotient or the product rule for this for sure.
The product. What we mean by a product is not just like this, okay? This wouldn't be considered a product rule. Explain the difference between something like this and something like this. When I say
I don't really know the
product
difference.
rule, I don't mean what's different between here and here. What is it?
Be simplified easier? I don't know.
The constant, okay, even this wouldn't be a product rule. Not exponents. Not just exponents.
Grouped terms.
Though these are group terms.
You have two different groups of terms with the square root.
Okay, different terms that involve what? Constants or variables? Okay, product
I
rule
see.
means we're multiplying variables. Okay, expressions that have variables in them. So this, do you need a product rule for that? No, no. That's just a constant. You could actually pull that outside of your whole derivative. The derivative of this thing is going to be 1 times 3. That's what it's going to be. Okay, derivative of x is 1, derivative of 2 is 0, 1 times 3 would be 3. That would be the derivative, right? So you get that even if you distributed the 3, that'd be fine. So we're not talking about products of constants times things. We're talking about products of functions in terms of x times functions in terms of x. Are you with me on this? Which is why we don't have to use the product rule when you find the derivative of that piece. That's just a constant times something. We're talking about functions of x times functions of x. You need to see the difference. Are you okay on the difference in that? You sure? So do we have a function in terms of x times a function in terms of x on that problem up there? Yeah, in fact, this is it right there. Let me erase that 3. You don't need that. Let's go ahead and let's try to set up the product rule. Now, could you distribute it and do the work that way? Of course. Yeah, of course you could. You could distribute this, it would be square root of x plus x squared square root of x. You would have to combine some exponents there, but then you could take a derivative. Not too bad. Maybe I'll show you that in just a minute. If we do the product rule, however, why don't you guys figure out how to write out the product rule. Set up the ddx of the first expression times the second, plus the first expression times ddx of the second. I want to see that on your paper. I want to see the work. I don't want to see just the answer, okay? At this point, you're learning this stuff. So I want to see every step. I want to see it written out just the way I've showed you. So derivative of the first times the second plus the first times the derivative of the second. After that, the calculus is done. Then you just got to do some algebra. So first I want to see if you have it set up right. Let's see, check your paper. What you have is the derivative of the first times the second function in terms of x. Do you guys all have that? Okay. Then we have what, a plus or a minus between them? It's always a plus. Plus product, product plus. Plus, what comes next? Do I need parentheses around that? I've told you how important parentheses are for this, right? Parentheses being multiplied by something that's important stuff. So have that times the derivative of the second expression. Show of hands, how many people made it that far? Great. If you made it that far, you understand the product rule. It's the derivative of the first times the second plus the first times the derivative of the second. We have that down. Now we just have to follow the ddx. The ddx is the calculus for us, right? That's the derivative at this point. So if you just follow that little piece, take a derivative piece by piece, you'll have the right answer. So understanding product rule, great. Then just do the ddx, okay. They're all going to be kind of basic derivatives that we've seen before. It's just applying them together within the context of a quotient or a rule, or a product rule, or we'll find out later a chain rule. Derivative of 1 plus x squared, what does this give you, please? Great, derivative of 1 is 0. Derivative of x squared is 2x times the square root of x. Plus, do I take the derivative of this? No. Okay, so 1 plus x squared, I'll leave it in parentheses, times, oh, derivative of the square root of x. Might want to change that, huh? So if we did, I'll write the extra step so you can see it. We do, yeah, x to the 1/2. If we take that derivative, that's 1/2 x to the negative 1/2. Did you get 1/2 x to the negative 1/2? Mm-hmm. Cool deal, all right, very good. Now, making it maybe just a little bit prettier, 2x root x, you could combine those with fractional exponents if you wanted to. What's on the denominator of this expression? On the denominator of this expression. On the denominator. There's a 2. There's for sure a 2 because of that 1/2. Do you see the 2? What else? Root x. Because x to the negative 1, that says denominator, and then the 1/2 says it's a square root.
Hmm.
1 plus x squared is on the numerator. Unless we want to get fancy and break that stuff up and find common denominators, we're just about done with that problem. How many people feel okay with this one?
Convert the square roots to fractions and then solve that.
Sure, we can do that as well. You'd have to distribute, from here you'd probably distribute that. You'd have 1/2 x to the negative 1/2 here, and you'd have plus 1/2 x to the 3/2.
And then you would combine that with your other, if you use fractions over there, because you've got 2
Yeah, we could do that. We could try that.
I think that's what I did. Yeah.
So this is 2x to, let's see, 1 plus 1/2 is 3/2. Plus, if we distribute, you'll get 1/2 x to the negative 1/2 plus 1/2 x to the 3 halves. And we're getting that because, of course, when you multiply those exponents, you add them. You add those exponents together. That's the 3 halves for you. So I've just distributed and distributed. 1/2 x to the negative 1/2. Half, and then 1/2, the x squared and the x to the negative 1/2 gives you x to the 3 halves. You all right with that? Then sure, you could combine these as well.
So you'd end up with like five halves over x to the 3 halves.
Yeah, 5 halves, x to the 3 halves, plus 1/2, x to the negative 1/2.
Yeah,
If you want to
that's
leave
way
it in terms of exponents, that's probably what you would end up with, is those exponents just like that.
And that's an acceptable way.
That's actually exactly what you'd get if you distributed this and then took the derivative. If you, just do it in your head if you want to, think about it. If you distribute this, you're going to get root x, right? Square root of x, the derivative of that is this right there. You see it? The derivative of this is this one. You follow? Distribute this, this is going to be x to the 5 halves. See the 5 halves out of that? X to the 5.
1/2 plus 2.
X to the 1/2 plus x to the 5 halves. That's what that is distributed. If you can't get that, do it later on your own, distribute that and figure out those exponents. This derivative is that piece right there. The piece of this derivative is 5 halves x to the 3 halves. It's right there. It's the same thing, same exact thing. Feel okay with this so far? All right, cool. Let me show you one more, and this really illustrates the idea of the product rule. And see if you can do it in general. Kind of a fun little problem, almost like a little puzzle. Not a hard puzzle, don't worry. This one time, I love my parents to death, but they gave me this one puzzle. It was, have you ever done a puzzle that doesn't have straight edges? Very difficult. It was shaped like a butterfly, right? And instead of having like normal butterfly, it was like a psychedelic butterfly, like, what do you call it stuff? Was it?
Tie-dye?
Yeah, it was a tie-dye butterfly with non-straight edges and a non-straight outline. I spent at least 18 hours doing it and then ended up burning in a fireplace. It's so ridiculous. It's not a puzzle like that, okay? This is like one of those 4-piece jigsaw puzzles you get in like 3rd grade, okay? Or no, maybe kindergarten. Puzzles, okay? You got it. Fun.
It's not like a double-sided puzzle.
It's not a double-sided puzzle.
That's not fun either. 2 different pictures on, different picture on each side.
Oh man, that'd be ridiculous. Not one of those either. No, it's this puzzle. You see, before, you could have gotten around this problem without doing the product rule. You could have gotten around this problem. This one, well, you might still be able to do that. However, it's going to be a little bit easier if you do the product rule with it. The idea is, what if you have this, and I tell you only 2 things about it? I say f of 2 is 3. F prime of 2 is negative 1. And I say find g prime of 2. That's my goal.
Okay, so product rule then. So we got 2x. Here, I'll write it out, like I probably should. Or it would be ddx. X squared plus 1 plus, or no, times 3 3 plus x squared plus 1 times d dx three. So we got 2x times 3 plus x squared plus 1 0. So we got 6x and plug in a 2. $12, I think. Alright, well, we'll see, I guess.
Okay, well, it's not too bad. What we're going to have to do, though, is figure out some pieces to fill in. We want to find the first derivative of g, and then fill in the 2. Do you follow me on this? So let's go ahead, let's use the product rule. Firstly, do you see why we need the product rule here? Do you see it? Do you see why? Do you have a function in terms of x times a function in terms of x? This is a function of x, yes? This is another function of x, and they're being multiplied. That's definitely the product rule. So what I'd like you to do, just follow the product rule with this. Go ahead and do that now. Follow the product rule. I want you to find g prime of x. Derivative of the first times the second, plus the first times the derivative of the second. Just write it out.
This would be g prime of x.
Derivative of the first times the second. Yes? Plus. The first times the derivative of the second. If you want to use d dx, you can. Would you agree that that is, in fact, the product rule for this problem? Derivative of the first, yep, times the second, okay, plus the first, got it, times the derivative.
I mixed up my terms, kinda. Try this again. Because you can't find g prime of x. Like I found it, you can't find it like that. This would be f of x, g prime of 2 you can find. So wait, this would just end up being 0, so I don't understand this actually. And never mind, I'm just gonna go back to my old answer. This is kind of weird. I'm not sure about this. I don't know.
for the second. I don't care that the function's not listed. It's f of x, so whatever that happens to be, that's what would go here, and that's what would go here, just like in our other examples. You with me on that? Well, let's do the derivative where we can. Give me the derivative of x squared plus 1. So this is 2x times f of x. True? Plus, do you take the derivative of that? X squared plus 1 still needs to be in parentheses, ladies and gentlemen, times, what's the derivative of f of x? Aha, f prime of x is how you write that. We don't have the actual function, but you know that...
Okay, I see. I'll move this down and delete it if it's wrong. So 2x times f of x plus x squared plus 1 f prime of x.
F prime of x stands for the derivative of f of x. Do you see that? Okay, cool. Now this, would you agree, is g prime of x? That's the derivative of g. That's what that is. What we want to find out is g prime of 2. What does g prime of 2 tell you to do?
Okay. Yeah, you can't find. This is as much. This is as good. This is as good as it's gonna get for g prime of x. So. From here, then you can start plugging in, probably. So 4 times 3 plus 0, I'm guessing. -1. No, okay, 5. Okay, I'm getting 7.
Everywhere you see x, plug in 2. Everywhere you see x, plug in 2. Everywhere. So
Including
for
f
that
of
means-
x. Okay, so that's
Tell
how
me
that
what I
works.
should have. 2 times 2, great, because x is 2, fantastic. Times f of what?
2.
That's everywhere you see the x, correct?
Okay, so yeah, this is wrong. Mhm.
F of 2. Plus, in the parentheses, tell me what else I got. Times f prime of what? Sure. Hey, what happened to all the x's? They became 2's. This x became 2, therefore every other x became a 2. Raise your hand if you feel like that so far. So it's kind of just a little exercise so you get used to the product rule and then filling out the numbers with the substitution. Let's go just a little bit further. There's no more x's. We can now make some substitutions. I know that this is 2 times 2, so that is 4 times, hey, what is f of 2? Have I given you that information?
3.
4 times 3. Plus this is all 5. 5 times, what's f prime of 2? Cool. Is it possible? Sure, yeah. They have to give you this though. They have to tell you what that is. I wouldn't be able to do this without that specific information. So all together, we're going to get
7.
Cool. 7. Ah, super fun. See, puzzle. I told you, enjoy it. Puzzling, why I find that interesting. But what did we just find? G prime of 2. Yes, that's exactly what we did find. What's it represent? Slope of this curve at that x value. So what you just found, this is actually a slope. The slope would be 7 of that curve, whatever it is, at x equals 2. Do you see that? Kind of neat. We're finding slope. Always keep that in mind. What you're doing is you're finding slope and you're finding derivative.
We still don't know what f of x is.
Nope. No, we might be able to figure it out. Or at least something that represents it, but no, we don't know. Hey, ladies and gentlemen, are you okay with the product rule? In general, it's really not that hard of a rule. If you have this down, that's it. It lets you break up a problem without doing distribution so that you can do it piece by piece, and that's the idea. Now we're going to look at the quotient rule. Quotient rule is just slightly more involved, but it's not that hard either. It's just a product. It's very similar to the product rule. Same idea. You ready to see it? The proof, again, is in your book. It's not hard to follow. Go ahead and just look at that when you get home tonight.
I don't have a book. Unfortunate.
Okay, so quotient rule. Quotient rule asks this question. Says, can you take a derivative of a quotient? Something in terms of x over something in terms of x. That's what this question is asking.
Well, yeah, but I guess you can, but it's gonna be in a special way. You gotta do it, the product rule.
And the idea is, well, can I just take the derivative of f and divide by the derivative of g? Do you think that's going to work? No, that never works. We can't separate derivatives by multiplication unless we use the product rule. We can't separate derivatives by division unless you use the quotient rule. Are you with me on that? You can't just take a derivative of the top and the bottom. That's never going to work for you. I give you a very simple example about how that's never going to work for you. If you did that, you'd get something over 0, true? Yet we know that this would be the same thing as 1/3 x squared minus 1/3, true? Derivative would be very easy there, 2/3 x, and that's it. So we can't just take the derivative of the numerator and the derivative of the denominator. That doesn't work for us. We have to have some other way to do it. By the way, you probably wouldn't, you could, but you probably wouldn't want to use a quotient rule for this very simple example. You'd probably break it up, just like I did here, and then you take a very easy derivative. The quotient rule and the product rule are really meant for some more extensive ideas, things where you don't have other ways to do it. And that's really the benefit of these rules. So I'll show you what the quotient rule says. Quotient rule says, okay, in order to take the derivative of a quotient, we're going to take some derivatives of each piece, but we're going to put them together in a unique way, just like we do with the product rule. It says you're going to take the bottom function times the derivative of the top function. I'm going to use some logic that's not quite mathematical, but it's going to make you remember something. Product meant plus, right? P with P. Product meant plus. What's the opposite of a product?
Quotient.
A quotient. What's the opposite of a plus?
A minus.
So what are you going to use here, a plus or a minus?
Minus.
Okay, it's not very mathematical, but that's the way you remember it, okay? Product with plus. Quotient, I think quotient has a straight line, so quotient has another straight line. Quotient minus, that's how I remember it. Actually, I remember it because I've done this so many times, I can't forget it. It's stuck in my head like jingle bells. I have a song for that too. The math song for Jingle Bells. Just watch my videos, you'll see it. Quadratic formula song, that's right. So the low function times the derivative of the high function minus the, or what I do, high function times the derivative of the low function all over squared. Or if you prefer, if you prefer. If you like the DDX format like I do. This says the same thing. That's the same thing. Oh, there is. There is, and you know what? I think I liked it, so I'm going to steal it from Michael. So he introduced it. Actually, I've heard it before, but it's a good. It said, what's it say again?
Low D high minus high D low, square the bottom, and away we go.
That's right. Very cool. Low D high minus high D low, square the bottom, and away we go. But you have to do this with it. Otherwise it's That's a Harry Potter version of this math. Yeah. Low D high minus high D low, square the bottom, and away you go. Yeah. Derivative of the bottom, derivative of the top times the bottom, or the bottom times the derivative of the top, minus the top times the derivative of the bottom all over the bottom squared. That's really what you're doing. Low D high minus high D low, square the bottom, away you go. Sound good?
Is the first one supposed to be the bottom, or can it be the top first? Yeah.
Hang on.
Can you do that?
You mean, can you interchange these two?
No, the side, from left with the minus sign, right.
Can you interchange these two?
Yeah.
Absolutely not.
Okay.
Because subtraction is not commutative like addition is. Okay, if you interchange those, is 5 minus 7 the same as 7 minus 3? I'm sorry, that's not even close to the same thing. It's 5 minus 7 the same thing as 7. No, so if I just interchange, like, wait a second, no, that's not even close. If I interchange these two things, no, they're still not the same. You can't take the top times the derivative of the bottom minus the bottom times the derivative of the top. That's what you're asking. You could interchange these. The derivative of the top times the bottom. Multiplication is commutative. That would be fine. Subtraction is not. So this is order dependent. Okay, you have to do it. That's not true with product rule, is it? That one, it doesn't really matter. But this one very much so matters. That's why I like the mnemonic. Low D high minus high D low, square the bottom. What do you got? You got it? Shall we practice it? I think so.
Oh, I thought you never were going to recite it.
No.
Okay. Let's finish this up.
Past that. I'm not gonna make you sing.
It's not a requirement of this course.
So you made us do in high school.
I did. This is no longer high school. We graduated singing. Now, let's look at an example. These are slightly different than the product rule because some of these examples can't be done without the quotient rule at all. You'll see it. By the way, you're going to find that the taking of the derivatives really isn't all that hard. I mean, you know pretty much everything there is to know at this point about taking simple derivatives, right? Move the exponent to the front, you take one away from it. That's a derivative of basic functions. Now it's just using the rules to split these up into little pieces to make them easier. So if you know the rules and the derivative, hey, you're good, you're fine, you're good to go. It's like you square at the bottom. Away you go. Okay. Anyway.
Let me try this one. So first we got low. Okay. 2x plus 5. We got D. We got high. And then minus high. So x cubed minus 3x squared minus 5. D low. Okay. Whoops, it's a bracket. Okay. Square the bottom. Sick. Okay. 2x plus 5 stays the same. For this, we got 3x squared minus 6x, and that's it. Minus stays the same. For this, we've got 2, just 2. And this at the bottom. Okay. Now we've got 6x squared minus 12x plus 15x squared minus 30x. Minus, this is gonna be a fun one, x cubed plus 3x squared minus, or plus 5 times 2. Okay. 4x squared plus 10x plus 10x plus 25, 12x squared minus 24x plus, you could probably combine some of these already, but I'm going to do it the harder way, 30x squared minus 30x, or minus 60x, minus 2x cubed plus 6x cubed, or squared, I wrote squared, plus 10. And then 4x squared plus 20x plus 25. What can we combine here? Looks like there's 110. Okay. So that stays. X is 60x. So negative 12x squared. Hold on. We'll go from high to low. So cubed. There's only one that I see. Negative 2x cubed. Squared. 6x squared. 30x squared. 36. 48. 38x squared. Minus 84x plus 10 4x squared plus 20x plus 25. There's no shot that this is it. I had to have messed up somewhere.
Now, this problem is slightly different than if I would have given you this. Look at the boards, notice the difference. If I give you that, there's something you can do with that.
Separate.
Yeah, that's separable. You can separate into 3 different fractions, simplify those exponents, then take the derivative of every single one. That actually might be the way to go for this problem. You with me? That'd probably be easier than using all this stuff, the quotient rule. Separate 3 fractions. I think some of your homework was like that, wasn't it? Separate it, simplify the fractions into, so combine exponents, and then take a derivative of each little piece, and that's fine. However, as soon as you do this, can you do that anymore?
Very complicated.
Well, you can. You can separate 3 fractions, but it's not
Help, though.
simplifiable like you did before.
Yeah.
You can't say x cubed over 2x plus 5 is one term. You can't do that anymore. You can't separate this 2x plus the 5. Can't do that. You see what I'm talking about there? Now, there might be a way if you multiply by the conjugate. No, still even that, it'd make it worse. Nothing good can come of this. Nothing good. The only thing we can do is understand that, hey, that is in fact a quotient, right? Does it fall into the category of the quotient rule?
Yeah.
Which means I have a function in terms of x over a function in terms of x.
Maybe it just does have a really
Do I?
complicated answer.
I wouldn't want to do it for this. That's not a function in terms of x. That would just be 2. That in that case, separate them. Man, that's so much easier. Don't use the quotient rule for stuff that you can do other things with. Usually, the other things are easier. So let's try to set up the quotient rule. Why don't you do it? If you know what, I'll do it with you the first one. I'll give you one in just a second to set it up because I want to show you how exactly I want it. For dy dx, that would be the derivative of y with respect to x. We're going to take low d high minus high d low all over the bottom squared, and then away or whatever that says. We're going to do that. But I do want to see your work. I'll give you a partial credit if I see that you know how to do the quotient rule, okay, which means I want to see every little step. You're learning this right now, and if I see wrong answers at the end, I want to see where your mistakes happened. So I want to see all this work. Understand? I want to see it. So we take the g of x, in that case, this is the bottom function, the 2x plus 5. The low, the d, the high. Low d high minus the high. What's our high again? And then the D low. Something like C low. You guys watch The Voice? Great show, by the way.
You get so sidetracked.
Yeah, some student earlier said, "Do you have ADD?" I'm like, I don't know. Look at that butterfly. over the low squared, the bottom squared. So we have, you don't need brackets, you use parentheses if you want. Low d high minus high d low, square the bottom, and you're done. Doesn't quite have the same. How many people can follow that though? Rich can. Right there. Notice how we've changed this quotient into something, well, these are very easy derivatives, very easy. You just have to follow the rule to make sure you get it to easy derivatives. Everything is pretty much going to be like that. Memorize the derivatives, know how to do the derivatives, memorize the rules and put them together. That's it. Nothing's too extraordinary. You know, just follow the rules that I give you and you'll be fine. I know I make it sound very easy right now, okay? Some of the rules, yeah, you have to really know how they interplay. I'll show you that as we get going, but if you understand the rules really well, the class becomes kind of a piece of cake after that. Does the 2x plus 5 change?
No.
Does the x cubed minus 3x squared minus 5 change?
Yes.
Follow the ddx, follow the derivative. Everybody, what is the derivative of this, please?
3x minus 6x. 3x squared minus 6x, yeah.
So far, so good? I don't want to see this garbage from you guys anymore. You leave that, I'm marking off points from you. Why? You absolutely must have parentheses. You're going to be distributing that in just a second. Okay, so you must have parentheses there. You leave me just this, I'm going to go, no, you don't understand what you're doing. That's different than this. So show me the parentheses where they're applicable. Does this change?
No.
There's no ddx associated with that. So x cubed minus 3x squared minus 5, okay. Does this change?
Yep.
What is that? Now, I don't need parentheses around the 2. Okay, that's just one factor. That's all right. But the other things, yeah, you got to have those. All
I still put
over,
parentheses
well, we're going to have
around
the
2 for
2x
that.
plus 5, and we're going to have a squared. Rarely will you distribute this. Rarely will you distribute this. This one, yes. We'll distribute this and we'll combine them. Rarely will you distribute that. And the reason is, if you can simplify it, you will. You'll try to simplify that thing. And it's already factored for you very nicely. Okay, you don't want to get the 4x squared whatever. Not plus 25, but you get 4x squared plus 20x plus 25. That's what you get. You don't
so
really
don't
need to
do
do
that,
that. Just leave it the way it is. This works out for us very nicely, especially.
Okay.
We start graphing these, which you're going to graph those without a calculator. It's sort of fun. Like another puzzle, double-sided butterfly with psychedelic colors. It's that type of puzzle, but it's still kind of fun. So not a throw in the fireplace type of puzzle. It's a fun puzzle. We'll talk about how to do that, and this form fits a little bit better for us. So we'll continue. Let's go ahead and distribute this. Can you tell me what you get when you distribute? Okay. I actually heard none of you. I'm just doing some ahead. Thanks a lot, guys. Appreciate it. That's okay. I know you know how to distribute. I'm going to do both these at the same time, the negative and the 2. So minus 2x cubed plus 6x squared plus 10. Do you see where the plus 6x squared and the plus 10 are coming from? Yeah. Okay, good.
Guess I don't know how to distribute because I got a negative 12x here. That messes me up a little bit. Plus 15x squared minus 30x minus 2x minus x cubed. Jeez, I really don't know how to distribute. How to get x cubed? Oh no, he just multiplied the 2 in there. Okay. He multiplied the 2 in there. Okay, he did it way easier. Get rid of all of this. Try this again. 6x squared minus 12x squared instead again, plus 15x squared, yeah, minus 2x cubed minus 6x squared minus 10 minus 2x cubed plus 6x squared plus 10 6x squared minus 12x squared plus 15x squared. These really all squared. Alright, so negative 6x squared, 11x squared, minus 2x cubed plus 6x squared plus 10. Forgot I need the denominator for all these. Two x plus 5 squared, 2x plus 5 squared, 2x plus 5 squared. Okay, so negative 2x cubed plus 17x squared plus 10 all over 2x plus 5 squared dy dx. You turn it into
Maybe a little
parentheses.
combined like terms here. If we combine some like terms, I'm seeing the x cubes. That gives me that 4x cubed. Awesome. Well, I got a whole bunch of x squareds going on, don't I? By the way, if I'm making a mistake, you let me know. I get, see, a 12, negative 12.
Wait a minute. This is a cube? Yeah, what? Dude, I'm terrible. What am I doing? Oh my goodness. It's not good, man. So what do we get now? 4x cubed. 3x squared plus 9x squared plus 10. Alright, we'll try it again. How many times am I gotta change my answer before I get it right?
Positive 15, positive 6. That looks like it's going to be 9? Oh, doubled that one. Minus 30x.
Where's the minus 30x coming from, man? I have all the terms except that. Oh, I didn't. Jeez, man. minus 30x minus 30x, delete this whole thing, 4x cubed, 3 and plus 9x squared minus 30x plus 10. Finally, man. Jeez.
That's your derivative. What did we just find?
Slope of a curve at a point.
What's this? What's that stand for? That's derivative. What's the derivative stand for?
Slope of a curve at a point.
Slope of that curve at what point? Whatever I want. So if I asked you to find the slope at x equals 1, could you do it?
Yeah.
Sure, you plug 1 into here to find the point. 1
Find the
comma
y
something.
value.
True?
Should give you
Then
the
you
point.
plug 1 into here to find the
Slope.
slope. You'd have a slope and a point. Y minus y1 equals mx minus x1. You can find the slope of that tangent line to that curve at that point. So this is still a slope formula. Now what you would do in general, you'd try to factor this and simplify it if you can. You can still do that. Sometimes that will help you. Now, when you have like an x cubed, don't really worry about that so much. Those are fairly difficult to factor in general. If you can, try it. See what you can do. Could you take a second derivative of that?
Yep.
See, you'd have to have another quotient rule.
Outside.
However, I haven't showed you how to deal with that exponent yet. So when you did low d high minus high d low, that d low would be the derivative of 2x plus 5 squared, right? So you'd have to distribute that at this point, or use a product rule within that at this point. Yes, you can use rules within rules. We're going to have a lot of that in this class. For instance, if I do rules, or using a product rule within that at this point. Yes, you can use rules within rules. We're going to have a lot of that in this class.
That's kind of
For
crazy.
instance, if I do a problem like this one, I'm not going to do this for you, I just want to give you a heads up. If I ask you to find the derivative of that, do you see how firstly there is a product rule?
It's used the quotient
Function
rule
of x times a function of x. That's
and
a
a
product,
product
rule.
rule.
Then when you go through that, as you're doing that, that's the first thing you see. From the outside in, you see a product
Oh
rule.
yeah, product
right?
rule first and
As you're
quotient
going
rule.
through the product rule, it would be derivative of the first, that'd be fine, times the second, still okay, plus the first, all right,
Once you get
times
to find
the
a derivative of the
derivative
second,
of
you
the
use the
second. And as
quotient
soon
rule.
as you get to the derivative of the second, how do you take the derivative of that thing? It's a quotient rule. You would have a quotient rule that is within the product rule. See that?
Yeah.
So we're going to talk a lot about this, how the rules will have an interplay, which ones you do first and which ones you do second. Basically, if you can follow the ddx, follow the first rule, then follow the ddx. And wherever you have a quotient, then you use quotient rule, or then use the product rule. We'll get there. Probably get there right now. Let's try one.
That wasn't much what segue, you know, I thought we had,
That wasn't my segue. It was a 2-second segue. Come on. That's good for me. I have ADD, apparently. I actually have the opposite of ADD. I focus only on math and other things.
Lady Gaga.
Good news.
Strange.
All right. Now, we're going to do this the hard way. We're going to do the hard way because I want you to see it. But there is an easier way to do this. The easier way to do this would probably be to distribute this, combine like terms, and then use one quotient rule, right?
The harder or the
To
easier?
distribute this, but there is an easier way to do this. The easier way to do this would probably be
Oh,
to
easier.
distribute this, combine like terms, and then use one quotient rule, right? But I want you to see,
Wants to
see
use the product
how
rule.
the product rule will play in this. Because
Yeah.
if I do one thing, you can't do it anymore. If I gave you like a 5, well, you definitely wouldn't be distributing that anymore, right? So you better learn the other way because I'm certainly going to give you something like that. You're going to need to be able to do it. So we're going to
Okay. So would you use quotient rule first?
learn how to associate the product rule with the quotient rule and use a rule within a rule right here. Now,
Let me see what happens. High. Or wait. I'm
when
actually
you
not
look
too
at
sure
the
on
first
this.
rule to use, you got to see which one's overlined, encompassing more of the problem. The product rule or the
Quotient
quotient
rule for sure.
The quotient rule clearly is. It says the product is actually within that quotient. Do you see it? So the first rule we're going to use is quotient rule. Let's write out the quotient rule. What is it again? Low D high. Low. What says my low?
X squared minus
Do I do anything to the low right now? Low, then what?
D high.
D high. So we're going to do D high. Oh, nasty. Low D high. And then what?
Minus high.
Minus. Okay, like the minus. Low D high minus the high. Okay. Real quick, I want you to look at the board here real quick. Make sure that when you distribute this, you still have a bracket. If you distribute, you still have a bracket because that negative will ultimately change those signs. You see what I'm talking about? That's important. So you wouldn't distribute the negative now. You distribute all this and then do the negative lastly. But you need a big old bracket around that thing. High and then D. Important. So if you still have a bracket real quick. Make sure that when you distribute this, you still have a bracket. If you distribute, you still have a bracket because that negative will ultimately change those signs. You see what I'm talking about? That's important. So you won't distribute the negative now. You distribute all this and then do the negative lastly.
That makes
But you need a big old bracket around that thing. High and then D. Low. All over what, ladies and gentlemen?
Oh yeah, I forgot that.
You're saying the bracket will go from the high and the derivative of the second? Yeah, okay.
Yeah. That thing like that. Because you distribute all that, and then the negative would go. Okay?
Can you just stop and like do a sidebar and do your product rule for your?
Well, we're gonna do this right now. So, but I need you to understand that this certainly is the quotient rule for us. Are you okay with that? That is the quotient rule. Now you follow your DDX. Don't change anything much at all. This isn't gonna change. X squared plus 2 squared, sure. This isn't gonna change except for that derivative. 3x minus 1, x squared plus 4, and that would give you a times 2x. Are you okay?
And then the derivative, 2x, that's it. X squared plus 2. Oh, and then this is the, this is when you want to use the product rule right here. I see. So d dx 3x minus 1 times x squared plus 4 plus, gotta move this over, plus 3x minus 1 times d dx x squared plus 4 squared plus 2. So the derivative of this would be 3. Just 3. Put a bracket over this. 3 times x squared plus 4 plus 3x minus 1. It's getting too big. Times 2x minus the rest. Alright, let me make sure he's doing that before I keep going, because this would be a lot to erase if I'm wrong.
Okay, on that deed yet? This is the rough one. Do you see what this does to you? So you'd say this is fine, x squared plus 2. Okie dokie, got that. Then you follow your ddx and go, I don't have to take the derivative of this, I do have to take the derivative of this. And as soon as you do that, do you see how that's like a problem within a problem?
Yep.
That is a product rule. Product rule says derivative of the first times the second plus the first times the derivative of the second. You'd get that. This one, well, we didn't change that at all. This one, we followed the ddx and just got the 2x. So I'll do this very quickly so you just get the answer that I'm looking for. The derivative of the first times the second plus the first times the derivative of the second.
Alright, this
That
is what
would
I
be
got.
your problem. Do you see how, oh, I did it really quickly. You would show your work off to the side and I should do the product rule. This is 3x squared plus 4 plus x squared, I'm sorry, 2x, the derivative of that is 2x, 3x minus 1. That's that little piece right there. So that's the product rule. After that, if you wanted to spend, I'd be impressed if you got down to this far, okay? That'd be fine. If you want to spend the time and distribute, and distribute, and then distribute, and then distribute, and distribute, don't forget the negative, and then combine all those like terms, use something pretty nasty looking, but it would be a polynomial in this case. Do you see the polynomial? Okay, I'm not going to go that far. It'd take me 10 minutes just to distribute everything. Do you
Alright,
understand the
that's-
idea
that
of
sounds
the
good that he's
product
not
rule
doing
working
that,
with the
actually.
push rule? Raise your hand if you feel okay with that. All right, very good.
Alright, and tomorrow, 40-minute video. And definitely not as bad as today, because I didn't finish the other one. So I had to finish that and then watch a whole 1-hour video. And this is number 12, applications of the derivative. Wonder what that means. Alright. And that's it.